Imagine this. You take 2 ice cubes. One goes into a glass of water, the other you leave on your kitchen counter. After a few minutes, something surprising happens. The ice in the water has shrunk noticeably, while the ice on the counter barely seems to change. At first glance, it seems simple. Ice is cold, water feels cooler than air, yet the ice in the water disappears faster. Why? How can something seemingly colder melt it more quickly? Today, we're going to uncover the hidden physics behind this everyday mystery. We'll dive into the microscopic dance of molecules, explore how energy moves invisibly through liquids and gases, and see how even a humble ice cube can reveal secrets about the way our world works. By the end, you may never look at a glass of water or an ice cube the same way again. To understand why ice melts faster in water than in air, we first need to understand heat transfer. Heat is the movement of energy from a warmer place to a cooler one. It's happening constantly around us, often invisibly. Every time you sip a warm drink, feel the breeze on your skin, or touch a cold object, heat is moving. Now, air and water both carry heat, but they do it in very different ways. Air molecules are sparse, floating relatively freely, delivering energy slowly. Water molecules, however, are densely packed and constantly moving. They bump into each other, swirl, and pass energy along efficiently. This is why water is an excellent medium for melting ice. It's like an invisible expressway of energy rushing toward our ice cube. To make it more relatable, let's use an analogy. Imagine trying to hand out flyers in a quiet library. People are few and spaced out. It takes a long time for the message to reach everyone. Now imagine handing out the same flyers at a busy festival where people are close together and constantly moving. The message spreads quickly, almost instantly. Heat works similarly. In water, energy spreads fast. In air, it drifts slowly. And here's the interesting part. This difference is not just about temperature. Even if the air feels warm, it's much less efficient at transferring energy to ice than water is. The dense, constantly moving water molecules collide with the ice at an incredible rate, breaking the ice lattice faster than air molecules ever could. Think about it in another way. Air is like a slow, meandering river, barely nudging a floating leaf. Water is like a rushing mountain stream, pushing and swirling that leaf along. The ice cube is the leaf. In water, energy doesn't just trickle in, it crashes around it, accelerating, melting in a way that feels almost magical, though it's purely physics at work. This simple observation sets the stage for a fascinating journey. A journey into the microscopic world where molecules are the real dancers and heat is their invisible music. Let's shrink down even further to a scale invisible to the human eye. Ice is made up of molecules locked into a rigid, repeating lattice, a carefully ordered crystal. Water molecules around it are free to move, bump, and swirl. Every collision between a water molecule and the ice lattice shakes the ice apart, transferring energy and gradually breaking the bonds, holding the ice together. In air, collisions happen as well, but far less frequently. Air molecules are spread out, moving slower and striking less often. So while ice melts in air, it does so at a leisurely pace compared to the energetic hustle of water. Here's a fun observation. If you stir the water, the ice melts even faster. Why? Because a thin layer of cold water clings to the ice, acting like a tiny buffer. Stirring removes this layer and replaces it with warmer water, allowing the energy to reach the ice continuously. It's as if the ice cube is being pampered in a tiny spa where warm molecules rush in to deliver comfort at record speed. Let's pause for a moment to reflect on how incredible this is. Every glass of water, every ice cube, every cup of tea, they are tiny arenas where billions of molecular interactions are happening simultaneously. Science isn't just in laboratories, it's in your kitchen, happening silently and visibly all around you. The mechanics behind this involve three primary processes: conduction, convection, and density-driven flow. Conduction is the direct transfer of energy through molecular collisions. This is why ice feels cold to the touch. Convection happens when a fluid moves, carrying heat along. Stirring water increases convection and accelerates melting. Density differences cause movement patterns within the fluid, which further influence heat delivery. Let's return to our analogy. Imagine standing in a crowded elevator versus alone in a hallway. If someone throws candy in the elevator, everyone gets a piece quickly because people are close together. In the hallway, the candy takes longer to reach everyone. Water molecules are the crowded elevator, air molecules are the hallway. Energy is the candy, and our ice cube is eagerly waiting. Now consider the amazing subtlety of nature. Even if the ice cube is small, and even if the water looks calm to our eyes, there's a microscopic frenzy of energy transfer happening every second. Molecules bump, swirl, vibrate. The dance never stops. This is what makes melting ice and water so much faster than melting in air. Another layer of fascination comes when we consider temperature differences. Warm water doesn't just transfer energy faster, it organizes the molecules' movements. Tiny currents form, circulation patterns emerge, and the ice melts not just from contact, but from the orchestrated flow of energy. It's choreography at a molecular level, invisible yet perfectly precise. And here's a subtle curiosity. If the water is very cold, close to the melting point of ice, it still melts faster than in air. Why? Because density and constant molecular motion matter more than absolute temperature differences. Water's structure, mobility, and interactions make it a superior medium for heat transfer. A simple fact hidden in plain sight every time you make a cold drink. So, what's the takeaway from all of this microscopic action? Ice melts faster in water, not because it's drawn to water, but because water is an highly efficient energy delivery system. Molecules bump, swirl, collide, and transfer energy continuously. Ice simply responds to the invisible dance unfolding around it. And here's a bigger picture reflection. Every moment of our lives is shaped by countless invisible interactions. The wind brushing your face, the warmth of sunlight, the cold bite of an ice cube in your drink. These are all tiny dances of energy and matter. Understanding them deepens our appreciation for the ordinary and turns simple experiences into moments of wonder. Science is not only about experiments in labs, it's about observing the everyday world, uncovering patterns, and realizing that even the smallest objects, a melting ice cube, a drifting leaf, a flowing stream, are part of a vast, interconnected system. When we notice these hidden patterns, life becomes richer, more fascinating, more alive. So next time you watch ice melt, imagine the billions of invisible collisions taking place. Imagine the molecular ballet, the swirling currents, the tiny delivery of energy. It's a world hidden in plain sight, waiting to inspire awe in anyone who stops to notice. Finally, I want to leave you with a simple question. What other everyday objects around you might be hiding secret physics? Try observing, experimenting, and reflecting. You might just uncover a hidden universe in your kitchen, your garden, or even in your own body. If you like this video, subscribe and join a growing community of curious minds. who love to learn, explore, and imagine the world in new ways.